Hello and welcome to another episode of the Oxford Online Maths Club. I'm James. It's just me today on the stream, but I'm joined in chat by Manna, who's helping moderate chat and might answer questions or talk to people. You met Manna on the live stream a few weeks ago. Manna was talking about surreal numbers. If you saw that episode, great to have you with us. I'm as always watching out for people who are here. Nicholas says they're here before the start. I think you're now here for the start. Hopefully I'm live. I think I'm live. It's kind of evidence that I'm not live, in which case you're not hearing this, so I can say anything. Erin's here. Hi, Erin. And I saw Kai. Kai's got some sort of train disruption. Cool. Okay. So I hope you're having a good time at the moment in school or not in school or whatever's going on. Yeah, belated Pi Day, everyone. It was 14th of March recently. Brilliantly here in the maths department at Oxford, our cafe is called Cafe Pi, and brilliantly they sold pie on Pi Day. It was amazing. Gabe's here. Hi, Gabe. Yeah, hi to people joining in chat. If it's your first time here and you're somehow on the YouTube live stream, you can also join chat. There's a link. It's on screen down there. There's a VFox code or something. Or if you head to the Maths Club website, we have a website when you can click the link to join chat. Johnny's typing in chat for the first time, so hi Johnny, welcome to the live stream. And hi to a few anonymous people. Again, you can be anonymous in chat if you want to. My plan for today, just me, my plan is to pick up on a problem from last week and solve a related problem twice. So we're going to try and solve a problem in two different ways. But first, I think I should check how your day is going. Let's find out. So, people who are new, I don't have a student to explain this to this time. Usually I'm explaining this to a student, but self-explanatory now, I guess. How's your day been? Let me know on a scale from 1 to 5. I've checked. I don't think it's possible to start the star rating thing here from 0. So 1 to 5 rather than 0 to 4 or something. And that is an interesting distribution to me already. Good stuff. Okay, so it seems like some people are having a good day, which is nice. Some people voted 2 stars. As always, I'm watching out for people who are not having a good day. Arjun's here. Gabe has noticed that as well as not having a student, I do not have most of my hair. Thanks for noticing, Gabe. Occasionally, I just get fed up of having as much hair as I had before, and I decided to have less hair. That is an example of something that's not interesting, and I thought I'd say it in an interesting way, and it didn't even come out very interesting. The average score has just hit exactly 4. I like it when it lines up with a whole number. It means that the balance there, and then it's gone. Okay, it looks like people are having a good day, which is nice. My plan's not very ambitious for the maths today. We're just going to do sort of one problem twice. I'm hoping it will be a bit sort of relaxed. I don't know what to do if we run out of after solving it twice. I don't know what we do after that. We'll find out, I suppose. Okay, people are voting for like the different options. I think that might be one of the highest scores we've had on the how is your day going vote. Somebody in chat appreciates the day polls. I like to know how people's days are going. I'm not really sure there's very much constructive I can say about the people who are having a 2-star day, which is, oh gosh, a few of you. Except, and I think I always say this, maybe doing some maths is the answer. If not, I'm going to do maths anyway. Okay, right. The average response has just tipped over 4 stars again, so I'm going to stop it there. Cool. Okay. I still have not worked out how to get rid of that. There we go. It's one of the buttons. One of the buttons removes that. Okay, right. So last week we had a problem with colouring in a cube, and this was related to something that we had going on. With Truchet tiles. We were thinking about putting Truchet tiles on the sides of a cube, and we wanted to know how many ways there are to colour in the faces of that cube, black and white. Oh, I just pointed out that I had an advert for the Matt live stream on the screen, and I forgot to say what was going on. Matt live stream is going to start in June. This is a similar live stream except we look at math problems. It's going to have very similar content to last year. The syllabus for the math hasn't changed. We're going to expand it a little bit. We're going to do more past paper questions than we did last year. So if you want to find out, chat about answers to past paper questions that you didn't see in previous episodes in that live stream, that might happen this year. That's based on feedback from previous years. People want to see more plus painters, so doing more of that. If you've already seen that live stream, then I reckon your time is probably better spent doing something different instead. But one of the unique features of this live stream is that we don't try and push you to watch the live stream if you don't want to. Right, okay, let's talk about this cube colouring problem. Black and white faces, and the crucial idea here is we're treating two colourings as the same if you can rotate the cube to get from one to the other. So thinking about rotations of the cube to get from one to the other. So in this top row here, I've got the cube that's all white, I guess, and if you rotate that, well, it's still all white. So this is no black squares, no black faces. And then next to it, I've got this cube that has one black face. And that's the only one I've drawn in this diagram, because if I rotate it, or if I had a different face coloured in, then I'd be able to rotate it so that it looks like this one with the black face on the top. Okay, so I've only got one picture with one of the faces of that colour. But then it's kind of interesting if I'm working systematically by how many of the faces are painted like this. When I get up to 2, there are choices. I've had to draw both of these here. Well, these have both been included in the picture that somebody else drew. One with the faces next to each other and one with the faces opposite. So it's kind of arrangements of where those faces are that's important. Arrangement matters. And this sort of systematic way of approaching it, so no, then 1, then 2, then we're going to maybe think about 3 and 4 and 5 and 6. It's a good way to work systematically like this, so that we know we don't miss any along the way. And we've already seen that maybe there are sub-cases depending on the arrangements within there. Milton Keynes, it's not that bad, it's got roundabouts. Navigate the roundabouts like normal. It's very grid layouts, very good for maths problems like New York. If you're watching from Milton Keynes, yeah. Good. Right, what was I doing? I was counting. So I think in this picture I need to point at these ones next. So these are ones with 3 black faces, if I'm counting like that. These ones next, and there's 2 possibilities here, which Colin has described as tennis ball, if they fit together like that, or corners if they fit together with the 3 faces on the corner. And it's a little bit tricky to see that I can't rotate one of those into the other. Or maybe that's not tricky. One includes an opposite pair and the other one doesn't include an opposite pair. And splitting down into the cases like that is how we might explore what's going on. Then we get to the case of 4, and it feels like that's going to be more complicated because it's more of the faces of that colour, until you realise that you can relax. If 4 faces are coloured in like that, then the other 2, it's exactly the same as having 2 of the other colour. So it's just colours inverted from those. So here, 4 colours inverted of the ones above them there. And that's why Colin, who made the picture, has laid it out like that, so that this bottom row is inverted from the top row. So here's 5 and 6. So in a sort of counting sense, I would go 1, 0, 1, 2, 3, 4, 5, 6, which is probably not how Colin was thinking of it when Colin put the picture together, but hey, there's a systematic way to get through them. So the total answer then is 10. Okay, which is quite a nice number. Okay, well, I quite like this problem because it's got this kind of systematic approach that you can use. You have to think about rotations quite carefully, and the faces. It matters what the faces are. It's not just 6 faces floating freely in space or something. It matters that they're on a cube because you have to think about the arrangement on the cube. So I quite like this problem as a kind of counting exercise. Okay, that's the one we saw last week. I think we did it quite quickly last week to try and get onto other Truchet tile things. I hope that's clear as why the answer is 10. I want to show you a different problem that's harder, and we're going to try and do it twice. The idea is very simple. What if we just have more colours of paint? What if we just have more colours? Oh, excuse me. What have I done here? I just want to move the text up. This week, what if we have more colours instead? Maybe 3 colours. Maybe instead of painting the cube black and white, we'll paint it red, green, blue. Would it be easier if you look at the net of the shape? That might be easier to... So it's easier to draw on the screen if I do nets, because the net is the 2D unfolded version of the cube. I find it harder to check whether things are the same, because the way I imagine these rotations is I imagine the cube sort of spinning through space to imagine whether it's the same or not. And I find that almost impossible to do when I'm looking at the net, because I have to imagine the net folding up and then rotating and then maybe unfolding a different way. And so the nets are maybe a good way of listing all of the things, but then identifying whether they're rotations or not is a bit tricky. Can I have suggestions about how we might approach this problem strategically? So if we've got 3 colours of paint available, it's possible you've seen this problem before. If you've seen this problem before, just sort of chill. We're going to do it 2 different ways. You might have seen this one way or the other. Let's say you've got to have some sort of systematic method. Can I have descriptions in chat, please, of how you would do it? I'm very original with my colours. How dare you? Fine, okay. Cyan, pink and magenta. Yeah, so trial and error is a good idea, actually. Trial and error can't really fail because there's only sort of a finite supply of these cubes. If we just paint faces systematically, then we should find all of them. Got a bit of a tricky job here to work out which ones match. Kind of identification. How do we work? Do we have to use all the colours on each cube? Great question. The answer is no. I want it to be a bit like this problem on the screen where I had 2 colours available, but I was allowed to paint things all the same colour if I wanted to. First time watching the live stream, welcome to the live stream. We're painting cubes today. Okay, you don't have to use all 3 colours. So your system might be to start with fewer than 3 colours. To start by thinking about the cubes that are don't use all of those 3 colours. That's message in the chat. Thanks to Manna who's moderating the chat. Combinations of different number of faces of each colour. Yes, that sounds like a halfway step, right? If we think about the combinations of colours for the faces, so maybe we do the painting on little scraps of paper ready to glue onto a cube. There's choices about what we could paint onto those little bits of paper ready to go on the cube, and maybe your 2-step strategy for painting a cube. Yeah, so 2 colour pairs, right, okay. Restrokes with 4 colours. I think there's white, red, green and blue is 6. I'm not sure why white plus red plus green plus blue is 6. Yeah, okay. If we use 2 colours, it's the problem on the screen. The problem on the screen is in black and white, but if we just use 2 colours, the problem is like that. We could change all the white and black squares there to red and green squares, for example. So, okay, I want to export that, I think. I think that's a really good suggestion. Anonymous person who said white plus red plus green plus blue equals 6. I'm not quite sure what plus means there. I don't know how to add colours together. I think you're probably using shorthand that you mean something, right? Okay, we'll find out. Let's talk about that 2 colour problem. So maybe one way to split it is ones that use all 2 colours and ones that use all 3 colours, which is a problem that someone suggested in the chat. Is it this problem that we have to do? And I think these are 2 kind of separate sub-problems. Ooh, if you don't have to use all the colours, it's kind of, you can use your previous solutions. Yeah, I would like to use the previous solutions. Yeah, 3. So Nicholas suggests 3 times the ones we've got, and somebody else says 30 with 2 colours, and I think I saw 30 before in the chat. So chat is suggesting that the answer to this one here is 30 cubes, like that. Can we explain that a bit more and double check that it's definitely 30? Yeah, we should have a reason, right? So to make sure we're being systematic. Yeah, so Nicholas, 3 times the one I have. Why are you multiplying by 3? Let's be really careful. Yeah, There's 30. Somebody else said 30. Oh, there's 30 just disappearing off the bottom of the screen. 30 from 2 colour pairs plus 1 colour. I should admit that I also wrote down 30 on a scrap of paper when I was trying to work out this problem earlier this week. Yeah, here we go. 2 colours is 10. Replacing sides of the 2 colours ones with a third. Oh, you're going to start working up to replace them with a third colour. I quite like that. Bring in the third colour, but just on maybe one of the faces or something. Is it less than 30 because of overlap? Yep, so Nicholas says you could use red green, red blue, or green blue. Those are the combinations. Gabe's thought that maybe there's some overlap. Okay. So what does overlap mean here? And actually Gabe's right, it's not 30. This is a mistake I made on my working out as well. There are 3 possible combinations of colours, agree, and there are 10 things on the screen there. So I think we're all imagining 3 copies of that picture, a red and green one, a red and blue one, and a blue and green one. Unfortunately, some of those are the same. Can you see why? There's a little bit of chat lag, so I know that. And also people have to type, I suppose. So, yeah. Aha! So, the problem is about using exactly 2 colours. Maybe you can see that in that thing we're imagining, yeah, these ones, the all white and all black ones, they're going to overlap between those kind of 3 copies I was imagining. But the red and green pair includes an all red cube, and the red and blue ones also includes an all red cube. So we sort of want to subtract those, but we do want to add them back in because we do want an all red cube. That's still allowed. We've got 3 colours paint. We can have an all red cube. We just shouldn't triple count it. Or is it double counted? Or is it double counted or triple counted? So maybe a good way to think about this is to split it down. Ooh, 10 plus 9 plus 8. Right, you should remove, Liam's thinking about removing them as you go through. These are no longer Truchet tiles. I think last week we had this on the screen because we were imagining sticking Truchet tiles onto the sides of the face, onto the faces of the cube. This week I'm not imagining any Truchet tiles. These are just painted cubes. Right, okay, so so it's something like 24. So within this, 24 using exactly 2 colours. This idea of splitting it down does work. That we've got 24 from the other 8 on the screen that genuinely use 2 colours. We can multiply that up by 3. And then there are 3 kind of solid coloured ones. So overall then, 27 here. This problem is weird. Truchet tiles were the topic of last week's episode. We talked about them last week. They're a sort of patterned tile. You put them down to make larger patterns. Sometimes you put them down at random and they make these kind of cool labyrinth-like pictures. Okay. Good, so we got 27. We all went for 30, but actually 27 because of the double counting. 27 that use 2 colours. I think it's time to engage with the ones that use all 3 colours. Yeah, here we go. Yeah, what about the ones that use all 3 colours? And I'd like to think about this in terms of sub-problems again. I quite like the idea from chat. This is not how I thought about it before, but I quite like the idea from chat about repainting one of the sides. It's a little bit complicated because some of them are going to turn out to be the same. If you paint over it, it might turn out to be the same. Like if you take these first 2 and you repaint the top face in the 3rd colour, then hey, it doesn't really matter that they were different before. You've repainted both of them to be the same 3rd colour. So it's not as easy as just multiplying by 3, unfortunately. Let's do some sub-problems within here then. I'd like to think about how many of each. I think this is a sensible way to split it down. Not certain, but I think this is a sensible way to split it down. What are the possibilities then? So if you've got a cube, the faces are painted red, green and blue somehow, you would like to count how many red faces there are, how many green faces there are, and how many blue faces there are. And you're using all three colours, so those numbers are not 0. What's the possible combinations that we could have? I guess I'm looking for some numbers that add up to 6, because there are 6 faces total. And I'd like the different possibilities of how to make 6, because I need to have a plan for how to paint all 6 faces, and I'd like all the different possibilities, because these are all going to be different cubes, right? If the distribution of colours is different, then they're going to be different cubes. That one's mostly red, that one's mostly green. I know that rotating them is not going to give me the same one. This one's got 3 blue faces, that one's only got 2 blue faces. They're not going to be the same under rotations, right? Because rotating doesn't change how many of each colour there are. Possibilities in chat. Yes. This is really hard to type, right? Because you need to get the white space, the spacing. So I realise now that was much harder to get you to type in chat than I thought. Let's get thumbs up, see if people. Those distributions between us, I think we're going to get them all. It's quite a sort of interesting sub-problem here to think about this kind of, how do you distribute your 6 faces between the 3 colours? You don't have to do it evenly, 2, 2 and 2. You could have more blue faces than red faces, maybe more red faces than green faces. I think the combinations in chat look good to me. So you could have 1 of one colour, 1 of another colour, and 4 of another colour. Kai's here. Hi Kai. Problems on the screen. You could have 1 of one colour, 2 of another colour, and 3 of the last one. Or I think you could go 2, 2, 2. I think that's all the possibilities. That's not obvious. This problem's hard because at every stage you have to engage quite a lot of brain cells, right, to check that you're not missing anything. On the way through, we had this trick of, don't double count the solid coloured ones. Down here, we've got this problem of how do you split this down into this? Yeah, do 3, 2, 1 and 3, 1, 2 count as the same? I think they sort of do, because, oh gosh, if you've got 3 blue faces, 2 red faces and 1 green face, that might be something different. What's 5c2? 5c2 is, is that how many ways there are to split it? It depends whether you count these 3, 1, 2 and 3, 2, 1 as the same or different. Let's say for now they're the same. We'll have to remember that you could switch the colours around. So 3, 2, 1 could mean 3 blue, 2 red, 1 green, or it could mean 3 red, 2 blue, 1 green, or one of the other possibilities. We'll have to remember that, but let's keep that sequence of numbers so that we're thinking about the possibilities of what those numbers are. Let's put them in increasing order or something. Yeah, I'm a bit worried that we might have 3 blue faces, 2 green faces and 1 red face, and then separately think about 3, 1, 2, and actually those could be the same under rotation, because when we actually paint the cube, that might be able to rotate so that the 1 and the 2 move around. Oh gosh, I think I'd like to treat them all separately and then count later. Okay, yeah, it's about doing listing the colours in a different order. We're going to imagine applying these paint schemes to, I guess, different sequences of colours. Wow, I'm not certain this was a great way to think about it, but here I am thinking about it, so let's go. Within those 3 possibilities, and I think that is all of them, within those 3 possibilities there are sub-sub problems to do with how we paint things. Let's go and zoom into those sub-sub problems now. So, first case, 114. This means we've got 1, let's say red, 1, let's say green, and 4 blue faces. Is there a unique way to paint a cube with those properties? Is there unique or not? So maybe it's unique. Maybe there's only one way to paint a cube and all the rotations then end up being the same. Or maybe there's multiple different ways that we could paint them. One way to think about this is, now at this stage we've gone out to the shops, we've bought enough paint, loads of blue paint, just a little bit of red paint, just a little bit of green paint. We're going to paint our cube. Does it matter how we do it? This sort of thing matters for doing things like flat pack furniture, where you get all the parts and then you have to assemble them, and sometimes you have to worry about whether, is there a wrong way to assemble it? Do the pieces fit together in something that will always turn out to be the right item if you rotate it around? Or can you put it put it together wrong. Connected and opposite gets a vote. Opposite or next to each other. Thank you, chat. Yep, chat's on this. I like this. Yeah, so not unique, and because those two special faces could be next to each other, or opposite. Okay. Kai wants to know if we should do nets. I mentioned this a minute ago, but just for Kai's benefit, I think drawing it 3D, I have to imagine it 3D to imagine the rotations. Mechanic things are the same if you can rotate it to get from one to the other. I can't imagine it with nets because I can't imagine the effect of the rotations on those nets. Yeah, red and blue, the shared edge or on opposite faces. Yeah, okay. Other than that, once you've decided to do 4 blue faces, a red face and a green face, that's the only possibilities. It doesn't matter whether you put like the red face on the top and the green face on the side. That's the same as if you put the green face on the top and the red face on the side, because you can rotate. It's impossible for me to imagine if I look at the nets. But red on the top, green on the side is the same as green on the top, red on the side, because you can rotate. Oh my goodness. Right. This problem's super hard. I've missed out the letter T over here. Okay. Okay, so we get two, what are we going to call these? Two configurations. And then each one of those we get to choose, when we go to the shops, we get to choose which paint is it that we're going to buy loads of. So there's kind of 3 colour schemes, I suppose. One where red is the majority colour, one where green is the majority colour. The other ones are going to buy one of each, so it doesn't matter what order I buy those from the shop. Oh my goodness, this problem. So you get kind of 6 varieties. I'm making up words as I go, I'm sorry about that. But like these 2 kind of configurations of how you put it together, kind of agnostic of what the colours actually are, and then you have 3 choices about what the colours are that actually matter. Oh my goodness, 6 varieties right here. Things get much worse. If you think this is bad now, things get much worse. Because I think it's time to think about the 1, 2, 3 problem. So there are 3 colour schemes. Oh no, how many colour schemes are there now? That's not obvious. Species of colour schemes. Not sure. For 1, 2, 3. Right, so just these suggestions of configurations coming in, of maybe you've been to the shops, you've bought 3, let's say red, 2 green and 1 blue, and you apply them to the cube, and here are some possibilities. Oh my goodness, there's quite a few in that chat comment. Let's try and draw some of them. There's kind of 2 things to think about. One is, on your way to the shops, which colour is your favourite? Does it matter? And then when you get home from the shops with your paint, how are you going to slap it onto the cube? Okay. So the suggestion here, you can put the blue. Right, okay, I'm going to try and draw some of these, I think. So the key idea, I think, is that the ones you've got 2 of could be next to each other, or they could be opposite. Oh my goodness. If you've just joined us, this is the hard way of doing the problem. The plan for today is that we do the problem in this absolutely awful method, and then if we've got any viewers left, we do it again in a better method. 6 colour schemes, yes, thank you. There are 6 colour schemes. I said 3 out loud, that was wrong. I gave it to chat, chat told me correct, there are 6. 6 colour schemes for this one. On this one, it matters what your second favourite colour is, as well as your favourite colour, because you're going to buy loads of your favourite colour, only 2 units of your second favourite colour, and then your least favourite colour, you're going to get 1, so it matters. Okay, there are possibilities though. So let's say you put your middle favourite colour on. Those squares might be touching each other, or they might be opposite. And then you've got your least favourite colour still to go. And your least favourite colour might go, oh my goodness. In this case it doesn't matter, it's going to go on one of these 4 around the middle. Doesn't matter which one, under rotations. So that's all, okay, that's 1 configuration. Happy with that. That feels like if the red ones are opposite, then the green one, doesn't really matter where you put it, because I'll spin it round. We might call that some sort of spinner. You can keep those red faces the same, spin the others. Okay, either both green, both of them next to it. It's hard as well if we're using different color schemes in chat comments. The other thing that's hard about this problem is that you can kind of swap the colors, except in a specific sub problem, you kind of can't swap the colors around because you're thinking about one of them or the other. There are sub problems over here. I promise you there's a better method after the break. Because the green face that comes in might be opposite over here on the back. So it might be only touching one of the red faces, or it might be touching two of the red faces by being here. And then I've got to think really hard about whether it matters that it's, you know, on the right versus on the left. That's the same because you can rotate 180 degrees around an edge. Oh my goodness, this problem. The question we're trying to solve is, you've got a cube, you've got three colours of paint, you're going to paint the faces. How many different ways are there to do that? Rotations count as the same. ECF does exist in the MAT. Okay. So down here we've got, oh my goodness, it's terrible. There are like three configurations. Zooming way back into this sub problem. There are like three configurations. So this is your middle favourite colour. Middle favourite colour opposite, and least favourite, least in between. And this is where your middle favourite colour are touching, and your least favourite touches both. And this configuration is where your middle favourite colour is touching, those two faces are touching, but your least favourite is only touches one. Oh my goodness, that's three configurations, 6 colour schemes. Oh my goodness, right, how many have we found over here? We found 18 varieties. I think. Keeping up? Yep, keeping up. Good, right. Oh, we're almost there, chat. We've got, how many have we got so far? 27 up here from the 2 colouring that we have to think about really hard. 6 for over there with a majority colour and 2 special squares. 18 down here, I have to think really hard about this one. So we've currently got 24, 40, 51 of these. Okay. And last sub problem to check is where we've got 2 of each. We decide we don't have a favourite colour. We're just going to get 2 of each from the shop. 2 red squares, 2 blue squares, 2 green squares, thank you very much. So there's only one colour scheme around here, which is to treat all of the colours equally. It kind of doesn't matter which one's your favourite, you are going to do this. You're going to do equally between them. So how many configurations are there? Once you come back from the shops with 2 blue squares, 2 red squares and 2 green squares, how do you put them on the cube? There are different options for how you might put them on the cube. To do with perhaps, let's say you take your red squares, maybe you put them next to each other, or maybe you don't. Let's see if we can get a chat to do this. I'll tell the story about how I approached this problem in between the 2 methods. Let's see. So give me some configurations, chat. I've come back from the shop, so I've got 2 red squares, 2 green squares and 2 blue squares. I need to put them on the cube. All of them opposite is such a nice idea. I love it. It works really well. All of them opposite pairs. It's so beautiful. It's the first one I thought of for my configurations around here. Just put all of them like beautifully opposite. Red, red on the back, green on the top, green on the bottom, blue on these faces. So nice. Such a nice cube. That one, out of all of these, that one's probably the nicest. All touching twins, or one opposite, 2 touching twins. Right, yeah, okay, so this is all op. All op. You could maybe think about having, I think, how are you describing this? All touching. So each pair of colours touches, and then maybe I'll colour in this green one here and this green one around the back, and maybe I'll colour in this blue one around here and this blue one underneath. we've got more suggestions in chat. All connected, yeah, so all of them touching, like connected to their matching colour one. All opposite, just one connected and one opposite. So Liam suggested somewhere. Yeah. Oh my goodness. I think all up might be some sort of orc, maybe. It's definitely not an elf. I think it might be, yeah. I don't know, it's the ending in a consonant for me. I suppose Elrond. Anyway, never mind. This is still the hard way. If none of them touch their twin, then they're all opposite pairs. There are a whole bunch of these though, where one pair is opposite, one pair are opposite, and the others are not opposites. So they come around like this. I call these ones spinners, I think. So this is like a red spinner with matching pairs. There are 3 of these because I can have a green spinner or I could have a blue spinner with matching pairs around the sides. Oh my goodness. And that is all the configurations, I think. 1, 2, 3, 4, 5. Except I'm wrong again. Liam, so Nicholas wants to go with Liam's suggestion. Liam's suggestion has 2 pairs opposite. There's something a bit weird that happens. This is really hard to imagine. So you get your red squares and you put them opposite each other, and then you get your green squares and you put them opposite each other. Let's say you do it like that. Turns out it doesn't matter how you do that. The blue squares you've got left over have to be opposite each other. There's no way to have the red squares opposite, the green squares opposite, and the blue squares touching. It feels like that should happen. But there's no way to fit all those things onto the cube. It's sort of really annoying that there's so many little distinctions between what does a configuration mean, what's the way that the squares are arranged with the ones that are the same colours is not quite the same thing as fitting all of those puzzle pieces onto the cube. So there's sort of a missing thing here with 1 pair touching, 2 pairs opposite because they don't fit on the cube like that. This is really irritating. Even worse, we've missed one. Would it be easier if we modelled the cubes as spheres? I think it might be even harder to draw. Even worse, we've missed one. We've missed one, and this is the one that I found last after an extra hour of thinking about this, which is in this sub problem down here, where each one is matched up with its pair. There's actually 2 ways here. Let's say I've painted the top one and this front one red. So I could paint the green one here on the side green, and then I could paint the bottom one green instead of the back one green. And then paint the leftover 2 blue. These 2 are different. They have the same number of red faces, green faces and blue faces. They have the same interactions between those faces in both cases. The pairs of faces are all touching the matching one. But you can't rotate one into the other. You can turn one inside out to get it to the other, but you can't rotate one into the other. I find this almost impossible to imagine. I just don't have the kind of mental rotation skills to do it. They don't quite rotate properly. It's not just a rotation. There are genuinely 2 different cubes on the screen there. One of the tricks to think about it is to mark the midpoints between the edges of the red, green and blue faces, and they either form a kind of right-handed basis or a left-handed basis. I guess people in chat don't know what bases are, so I shouldn't have said that. Yeah, it's pretty bad. It's a turning inside out kind of relationship between the 2. The one on the left is the last one I found. And at this stage I really got fed up with the problem. This brings us up to a total of, so I don't know if I even call these different configurations. It's got a bit painful at this point. There are kind of several things going on here. I think over here, from this 222 case, I think we gain, let me think really carefully, 1, 2, 3, 4, 5, 6 varieties. counting those 3 spinners, the one all opposites, and the one with the 2 here, the 2 with all pairs touching, which gives us a grand total then of 57. This is the bad way to do the question. This is the slow way to do the question. As far as I know, and I've seen people try this on the internet, but I've never seen anyone try it like this, to actually just go and do the problem. So here's the pivot. For 20 minutes now, I want to show you the fast way to do the question. It uses some university mathematics, and actually the only examples I can find on the internet of people trying to do this problem, they do it as an example of this theory. So I think this might be the only attempt on the internet right now to actually go through and do the hard work of actually finding all of the cubes. There's this other method which is going to give us the answer 57 without actually drawing any of them. Okay, this is kind of the advert for the next 20 minutes. We're going to get 57 in a different way. How did I get 57? Final step then, just to point it through. We had 27 that were 2 colours. We had 6 over here from the 114. 18. This feels like the Lord of the Rings again. I'm listing random numbers. 18 from having 1, 2, 3 as our colour scheme kind of breakdown, and then 6 over here. 2. These are called a chiral pair. Chirality is like left-handedness and right-handedness. A chiral pair here is the pair that are different. There's a sort of left-handed one and a right-handed one. The all opposite one, and the 3 spinners was another 6. Adding together 6, 18, 6. Oh, please tell me I've done this right. Yep. And the 27 at the top is total 57. So overall, 57 varieties. Woo! Including using only 2 colours. 30 if you don't count those. If you have to use all of them, 30. 27. Right, okay. Let's do the other theory. I'm not certain how much I'm going to say about it. I want to give you an idea of what the theory is. I mean, it's university maths, but part of the idea of this show is that we see some idea of university maths. Don't think I'm going to teach you the university maths, because if you want to learn the university maths, hey, probably going to end up doing a university maths course if you're that excited about learning this theory, and you'll learn it at that stage. So, yeah, Liam gets it. Do what James did and draw many cubes. Yeah, okay. The reason this method is nice, and the reason you should tune into the next 17 minutes of this stream, is that it also answers the question for 4 colours, and in fact n colours. At this point, 4 colours would be a completely impossible task for us, because we'd have to do so many sub-problems and so many cases about the different configurations and colour schemes and combinations of numbers and faces of different colours, that I just don't want to do the 4 colour thing. This method is going to do this problem for n colours, and it's also more widely applicable to other problems with rotations and other symmetries as well. Let's go. So, the idea is to think about a point for each painting of the cube. Don't worry about rotations yet. So if I just paint the faces of the cube in my 3 colours, I want to paint the 6 faces. I'm going to do a little diagram of these. Rather than drawing all of those, I'm going to just put little dots. How many dots do I need? How many possibilities are there? No sub problems in this one. So I've got 3 colours of paint available. I'm just going to paint the faces. Just don't worry about the rotations. Step 1 here is supposed to be, a much more relaxing problem if you don't think about the rotations. So these are going to be, there's quite a lot of them. So these are going to be like stars or like points of light in the sky. That was a bit overly philosophical. How many? Waiting for chat to tell me how many. Chat told me? Yeah, 3 to the power 6. Yeah, thanks, chat. That is quite a lot. So, yeah, Nicholas, we're gonna forget that we know it's 57 for now. Forget that we know it's 57. Forget anything to do with the rotations and the first thing that we did. This method starts fresh from just throw away everything and get me some new cubes, quite a lot of them. So I'm going to put spots down for each of these 3 to the 6 possibilities. Gosh, 3 to 6 is some huge number. It includes loads of stuff like the entirely red cube. It includes the one where the top is painted green, and it also includes ones where the side is painted green, but the others are all red. So yeah, that's quite a lot, right? Is it 729? I guess that's not too big. I'm not going to do 729 dots. Step 2 is to join 2 dots if they're related by a rotation. Okay, so let's say maybe this one is the one that's green on the top and it's related to the one that's painted green on the side because I can do a rotation. It's also related to the one that's green underneath because I can do a rotation, and the ones that are green on the other sides. So there's a little bit here of joining these dots for these different paintings when we just threw the paint on and did all different paintings. And they're related by rotations. Don't really care what the rotation is. I'm going to join them up. Okay. So ideally, in a beautiful world, we would just divide by 6 because these things would always. I would love it if they always turned up in packets of 6. If they always came in 6 packs, then that'd be great because we could just divide by 6. You'll notice that this is not the answer because 729 divided by 6 isn't even a number. So that these constellations, which are also sometimes known as orbits, which I guess is a bit confusing because it's a different astronomy word, but hey, they're different sizes. For example, the one that's got red on the top and the bottom, so the one that's got red on top and the bottom is related to some other paintings that I've got going on. It's related to the one that's painted red on the front and the bottom, and it's related to the one that's painted red on the sides. So there's only actually 3 things in that constellation or that orbit. And the one that's just all red lives on its own. That doesn't get connected to anything because as you rotate it, you always get back to the same thing. Is it graph theory? We're not actually going to do any graph theory. I'm just drawing it like a graph. Sometimes this is easier to imagine. Okay, they're complete graphs, sure. So if you can rotate from this one to this one, from A to B, then you can also rotate. If you can rotate from A to B and you can rotate from A to C, then you can also do some sort of complicated rotation where you rotate from here to here. So you can do all of these sort of compound rotations. So to get from B to C, sorry, I did that way too fast. To get from here to here, we can sort of undo that rotation and then do that rotation. So these are all kind of really complicated graphs where everything's interrelated. I'm not sure I've drawn all of it like, but hey, everything's rotated. Okay, so what we really want to count, really want to count the orbits. So these little constellations that we have, we want to know how many of them there are because we're considering things to be the same under rotations. So we did all this kind of sloppy, do all the possible 729 different paintings. And then realise that some of them are the same, and they live in different sized orbits. Here's over here the orbit or constellation for all green is over here, all blue over here maybe. This one's sort of 1 red, 5 green. It comes in this kind of 6-pack, but they're in different sizes. So they get connected if they're kind of physically the same cube. You maybe, I don't know how you did this, right? Maybe you painted 2 cubes and then you go, that's the same. It's the same. I painted the top on that one, I painted the side on that one, and then I dropped them all, and those are the same. Okay. Yeah. So we're going to try and find the number of these orbits or constellations. How many constellations are there in the sky? Things that are connected. There's some really nice theory that I think I'm going to explain very loosely. Um, for most of these, there are some rotations which give you back not just the same physical cube. I mean, rotations always give you back the same physical cube, but sometimes rotations give you back the same painting in that set of 729 paintings. For example, here maybe this is the one with red on the top. So this was the label. This is the label for the whole constellation, and maybe this is just now the label for just red on top. If you have red on top and you rotate it, then about an axis that goes through the middle of the top, then you get the same. You get the same paint. You get the same painted sort of shape. That rotation doesn't affect anything. So I guess I'm saying that this one should be connected to itself. So there's sort of some loop here. These things are all connected to themselves. And actually worse than that, because as well as rotating by 90 degrees, you could rotate by 180 degrees. This one's red on the top, green everywhere else. So I could spin it around 90 degrees or 180 degrees or 270 degrees. There are quite a lot of these loops. So if I draw multiple loops, because each of these has got some spinning that it can do, that say actually there are lots of different rotations you could do to count that get you back to the same painting. So this dot is related to itself by a non-trivial rotation, or I guess some rotation. Okay, it's also joined to itself by the trivial rotation, I suppose. If you count the trivial rotation where you don't spin anything, as keeping it all the same, then that's a rotation that always loops back to itself. And these lines in between things are complicated as well, because there's different possibilities about how you rotate one to the other. So I was describing how this one's maybe red on the top and bottom. To get it from that to red on the sides, you could do just a simple rotation, or you could do a bit of flair. You could rotate it and also spin it around the face. Those are all green, so fine, just spin it around. Those are both allowed. So there's kind of multiple ways that you can get from one to the other. So this is maybe not quite a graph so much as a complicated kind of multi-lane highway with lots of these extra loops that point back from a star to itself. Kind of looks less like a constellation now, because in constellations people never join the same star to itself. But hey, that's what I need right now. For time, I'm gonna point out that if I keep drawing all of these lines, I'm going to draw some huge number of lines total. I have this really ambitious plan, I suppose, to take all of those points and join them to all of the things that they're rotated to, related to by rotations. There are 24 possible rotations. And I'm going to skip that and leave that as homework. In school, at some point, you learn about the rotational symmetries of a square, right? You can rotate a square by 90 degrees or 180 degrees or 270 degrees, or you can leave it alone. For cubes, there are 24 rotations. So I'm going to draw a lot of lines. I'm going to draw 729 times 24 lines. Okay. Which is quite a lot, so I'm not actually going to draw them all. Here's the bit of university maths that makes this actually worthwhile. And in fact, at university, nobody's really got this picture in their head, really, while they're doing this, because the punchline is so quick. So I'm aware this is a thing where I draw a complicated diagram and then I tell you a punchline that kind of feels almost unrelated. And it works like this. In these constellations, the number of things that fix this element, the number of loops, I don't know what to call those, self-looping rotations, multiplied by the number of elements in that orbit, the sort of size of the constellation. Let's go size of the orbit is equal to the size of the group. The size of the is equal to the number of rotations total. Whoa, that came out of nowhere. Let's explain this a tiny bit. let's explain this a tiny bit. It turns out that I'm drawing these kind of multi-lane highways here, where I've got maybe a certain number of things that leave that alone, leave this configuration alone, and I've got a certain number of things that change it to something else in the constellation. So I've got some number of things that keep the red square on the top and just spin it around so that we've still got a red square on the top. And I've got some number of ways to take a red square on the top and turn it into a red square on the side. And the number of those is related. The sort of rotations with flare, where you turn it over and also spin it, there's the same number of those as there are just spinning it on its own without doing the sensible turn first. It turns out there's the same number of things that keep it the same versus things that transform it into a particular target. Essentially because the ones that don't do anything, they are the self-looping ones, the ones that really don't do anything for this particular painting. The ones that don't do anything, you could do a sensible rotation and then one of the stupid ones that doesn't do anything. And you have sort of free choice of which one of the stupid ones to do. There's kind of this reason about why these highway things, if there's 3 looping things like I've drawn here, then all of these connections have 3 lines in as well. Because this thing is connected to everything in its constellation and itself, if you multiply together, you'll get everything. All the possible lines coming out of that either go to itself or to one of the other things in the constellation. Overall, so the same number going to each element. So it turns out to just be the complete graph with every line in, but multiple times, also self-looping. Right, cool, that was awful, wasn't it? That was really bad. Did not do a good job of that. Punchline. The number of self-looping things multiplied by the size of the orbit is the total number of rotations. I know the total number of rotations. There's 24 for a cube. That's nothing to do with painting. That's just a fact about cubes. There are 24 rotations of the cube. Here's the clever bit. If I count for each of those rotations, how many points does it keep fixed? How many self-looping loops do I draw for that particular rotation? So maybe I imagine, in abstract, I imagine rotating by 90 degrees about a line through the middle of one of the faces. How many paintings does that keep the same? So it's the ones where it's maybe a colour on the top, different colour on the bottom, and the ones around the middle have to all be the same. So that when I do that rotation by 90 degrees, I get the same painting. If I count how many self-loops there are, I can then use the formula on the left to convert that into something to do with the orbits. In particular, if I add up the total number of self-loops and divide by the number of rotations, then you get exactly the number of constellations. So the plan is to do the adding up over all of the rotations. This is going to be a bit messy. Adding up over all of the rotations, the number of points that are fixed by that rotation. Add up all of that and divide by the number of rotations. That is the number of orbits. And this is really good because there's no sub-problems, there's no sub-cases really. You think about the rotations, you think about the effects, and what would that keep fixed is so much easier to think about than what are the weird kind of side cases. Infinite amount of self-rotations, not for a cube. So spinning it around, there's 24 rotations. No sub-problems, just think about these things that are kept fixed. You can do this for any number of colours. The counting problem is much easier in that case. And it turns out that, maybe this is enough to get people back on board with this as a sensible idea, that the final answer is thinking about these 24 separate rotations, which is really not that bad. I am running out of time, so I'm not going to think about my separate rotations. 8n squared plus 6n cubed or something like that, where n is the number of colours. Put it on the screen, we've got a polynomial. This is ridiculous. This is the answer not just for 3. If you plug in 3, you get 57. If you plug in 2, you get 10. If you plug in 4, you get, I can't remember, some huge number for how many different colourings there counting rotations, it's the same. And it works by kind of thinking about the effects of those rotations. Do they cause things to stay the same or to be matched up? And if you keep track of the matchings and staying the same just right, then you can do that. So 4D cube, you can do a very similar analysis, except you'll need to think about all of the possible rotations of a 4D cube, which is a little bit harder. Cool. This thing's got some names. I thought I'd tell you the names. So this kind of formula over here, it's sometimes called Burnside's lemma. That's a bit of a terrible name because Burnside didn't invent it. So some people called it the lemma that is not Burnside's because Burnside didn't invent it. I kind of get where this is coming from. It's clever, it's funny, but it doesn't help you remember what the thing is. I call it the orbit counting lemma, because it's a lemma that helps you count the number of orbits. Cool. Okay. So there are quite a lot of YouTubers who have done the second method, where you try and teach Burnside's lemma, and maybe you even call it Burnside's lemma. And I've seen lots of people online do it like that, but I've never seen anybody do it the hard way of actually working them out, which means that I've never seen anybody else actually show you all 57 cubes. So I thought I'd finish by showing you all 57 of them. Here they are. This is a video of them spinning around. This is the 57 ways to paint a cube in 3 colours. The lemma that's not Burnside's, the orbit counting lemma, doesn't actually construct these for us. To actually draw them, actually put them on the screen for you, I think I had to do it the hard way and actually work out what they all were. Okay, so is this, questions in chat. Neat relation with the solids dual and octahedron, yeah. So octahedrons have got the same rotations, which means you can reuse some of the maths. The painting's different because it's got different number of faces, but it's not that hard. There is going to be further reading for this one because I have more stuff I've run out of. And if you're keeping up with further reading, we posted some more further reading on the Maths Club website recently. The further reading looks like this on the Maths Club website. Come on, load. There we go. On the Maths Club website, looks like this. Most of the episodes in this season now have some further reading. If you click on the further reading, you get things like other diagrams, other stuff going on, links to Desmos things, links to books and other sorts of maths that we've thought of. We've got this for almost every episode in this season. The aim is that by the time the season finishes, they've all got further reading for this season. So keep tuned on this page. Some of the ones that are missing will get filled in at some point. What's a good one? Oh, I quite like the pentagon one. Pentagon geometry one has got some stuff in. It's got Pascal's triangle. Carlisle circles and stuff. Cool, right. Other stuff that you might be interested in. And now that I've mentioned it on the stream, the rule is that I have to go and make it for this one, so that maybe I can tell you more about this. I've got a resource somewhere where I've got nets for all 57 of them. So people have been asking about nets. If you want to download a copy of the nets for all 57 of these cubes so that you can print them out and make them, I don't recommend that at all, but I'm going to put it in the further reading. Right, good, okay. I'm a little bit over time, but hopefully that's good. Anyone else? Yeah, it's not good to look at. Sorry for making you look at that. Guys lost. 57 is a small number. Irv wants to make them. There we go. I'll give Irv. I'm going to put the nets in the further reading. Good. Okay. Yeah, they're not pleasant, are they? There's something about the video. It's something about the pulsating nature of the way they go in and out. Don't like that. Aaron's going to read this. Yep. Take care then. See you in about 167 hours or thereabouts. Is it daylight saving time? Is that why I actually said? Hang on. I've got to get it right. I've got to look it up. Oh, no, daylight saving time is more than a week away, so it really is 167 hours. Okay. For people who watch outside the UK, we do this thing called daylight savings time, where occasionally we all change our clocks and it throws everything off. Right, cool. Thanks everyone. Take care. Have a good evening. We'll see you next week. If you're watching the live stream, maybe try and identify the exact moment where I realised I did not have time for the thing I was going to do. Take care everyone, bye. As always, don't know how to, there we go, bye.